a much nicer way to classify stationary points is to calculate the second order derivative. But for that, perhaps we should define what a second order derivative really is. Second order derivative is very simply defined as the derivative of the first one. In Newton's notation, we write the second order derivative like this, or you can also use two dots at the top. And the way we define it as the derivative of the first derivative, you can write this, for example, in this form. You could write it in this form, which means taking the derivative of f. Or we can also write it with 2f divided, and this is divided by dx to the power of 2. This is important in terms of notation because the second order derivative is an operator. So you can think that what you're doing here is applying this operator, which means differentiate twice in respect to x of a given function f of x. This is how you should be seeing it. All these notations are equivalent, and again, provided you're consistent, you are free to use whatever you prefer. Second order derivatives are quite useful to classify stationary points. If we think back of a general point x equals c, if you remember from a previous video, this point is said to be stationary if the first derivative at that point equals 0. And if we calculate the second order derivative, we can actually use it to classify it. How do you use the second order derivative to classify a stationary point? It's relatively simple. You first calculate it, and in general it means calculating the second order derivative for any point, and then you look at the value when x equals c. When you do that, you essentially have three different cases. Case number one, this quantity, the second order derivative at x equals c, is higher than 0. Case number two, this quantity is lower than 0. And say case number three, this quantity equals 0. So this is exactly the same thing. What does this imply? In case number one, if the second order derivative is higher than 0, it means the function is growing at that point, which means that this is a local minimum. And for similar reasons, if the second order derivative is lower than 0, it means that you're in the presence of a local max. The problem is when the second order derivative is 0, you can't really tell what's going on, so you need more information, such as evaluating the sign of the first order derivative just left and right of your stationary point. There's nothing like a concrete example to test your understanding and what we've just covered for a general case, so let's try to do it. You can also find this example in the lecture notes at section 6.3, and the function that we're going to have a look at is f of x equals x to the power of 3 minus 3x. The goal here is to try to find the stationary points and then to try to classify them. And we already have all the tools that we need. First of all, step number one is to find the stationary points. We need to find at which point the derivative is 0. So it means that first of all, we should be calculating the first order derivative. And because we're going to use it to classify stationary points, we should probably get the second order derivative already as step number one. Now this derivative is relatively simple. You get 3x to the power of 2 minus 3. This is the first order derivative. and we can differentiate it again. That's just the derivative of this expression. That's what second order derivative is. And in this case, you'd get 6x. This is your typical step number 1. Step number 2 is you want to find the stationary point. This means finding a solution or solutions for an equation of this type. You want to find the solutions, the points x for which the first order derivative is equal to 0. For this specific concrete example, we want to solve the equation 3x to the power of 2 minus 3 equals 0. Fortunately, this is a relatively straightforward equation that you can manipulate. Take 3 to the other side, then you can divide by 3, and you end up with 2 solutions which are plus and minus 1. If you're dealing with a problem in physics, like describing the real universe, and at this point you're dealing with quantities such as mass, you probably want to skip the negative solution. But because we're now doing a general case and we're not saying what we're actually looking at, we'll keep both solutions. This means that at the end of step 2, we've now found all the stationary points. This is because only these points, plus 1 and minus 1, are solutions to this equation. The final step now is to try to classify these stationary points that we could call P1, and P1 is x equals minus 1, and P2 being x equals plus 1. How do we classify them? The simplest way is to use a second order derivative, so we can do step number 3, which is classify them. In order to do this, what we need to calculate is the value. Actually, we only care about the sign of the second order derivative at a specific stationary point. Let's start with P1. For P1, if we plug in x equals minus 1 to the second order derivative, we actually get, and I'll write it explicitly here so that it is clear, we get minus 6. Minus 6 is below 0. This implies we have a local max. For the other stationary point, that's P2, the second order derivative at x equals 1, that's the second stationary point, will be similar but with the sign being flipped. That's positive 6. This is higher than 0, therefore it implies we're in the presence of a local minimum. And that's it. These are the simple steps you should be taking to find and classify stationary points of a function. In this case, it depends on just one variable. To recap very briefly, step number 1 is calculating the first order derivative and the second order derivative. Step number 2 is to solve this equation to find all values for which the first order derivative is 0. Once you find the solutions, your final step is then to classify these points, which means calculating the sign of the second order derivative for those specific points. In this case, we found that there are local maximum and a local minimum. Once you find the stationary points and whether they're local minima and maxima, you actually have all the tools you need to sketch a function, the general behavior of the function, which is crucial to solve and interpret a range of problems, specifically in physics. Therefore, let's have a look at some really good practices of how to sketch a function, and specifically thinking about this function and the information we just gathered about it.